Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening, I'm Yvonne Stapp for Science for the Public, and I welcome you to tonight's Contemporary Science Issues and Innovation program. Tonight, we have the pleasure of talking with a real innovator in astrophysics, Dr. Scott Kenyon. Dr. Kenyon is a senior astrophysicist at the Harvard-Smithsonian Astrophysical Observatory. He received his PhD in astronomy from the University of Illinois, Champaign-Urbana in 1983. He joined the Smithsonian Astrophysical Observatory first as a postdoctoral fellow and then worked his way up over the years to senior tenured position. Dr. Kenyon has made a number of significant contributions to astrophysics. These include the evidence that even very young stars of 1 million years or so can accrete enough material from surrounding gas and dust to form planetary systems. He's especially well known for his innovative computer code called Orchestra, which is one of the leading codes for simulating planet formation. His calculations were the first to demonstrate that the debris disks around the nearby stars are newly formed planetary systems containing planets at least the size of Pluto and Mars. His monograph on symbiotic stars and his work on runaway stars are standard reference works in astrophysics. Dr. Kenyon is a fellow of the American Association for the Advancement of Science, and a fellow of the American Physical Society, and a member of other distinguished scientific societies. His awards include the Copernicus Medal in 1987 and the Hoops Prize of Harvard, shared with two others, in 1995. We are very honored indeed to welcome Dr. Scott Kenyon. Welcome, sir.
It's a pleasure to be here, Yvonne. Thanks for having me.
And let's start with the stars.
Sure.
Tell us about star formation, if you will.
Sure. Well, if you go out on a nice dark night in the middle of winter, and you can actually see the stars, you can see the Orion constellation, which is a hotbed of star formation. And in the, Orion is a nice parallelogram constellation with 3 stars in the middle of the parallelogram, and the 3 stars are the belt of Orion, the hunter. And below the belt are another set of 3 stars, which is the sword of Orion. And in the middle of the sword is the Great Orion Nebula. So the Great Orion Nebula is in the middle star of the sword of Orion. And what you see here is a bunch of red gas, which is all hydrogen gas, which is caused to glow by high-energy photons emitted by the bright stars in the center of the nebula, which is in the middle here, in the big white spot
white area,
where you see you can see a bunch of stars if you look really closely. And every one of those stars is only 1 to 2 million years old. And so what happens here is the cloud is a big, what we call molecular cloud. It's of molecular hydrogen, so 2 hydrogen atoms formed together as a molecule, a bunch of helium atoms, and trace elements, which is all the stuff we're made of, carbon, nitrogen, oxygen, and silicon, and so on. And so this cloud is a big cloud. It has enough material in it to make 100,000 or maybe 1 million stars. And little bits of the cloud become gravitationally unstable, and they collapse. And as the cloud collapses, since it's rotating a little, just like when an ice skater brings his or her arms in and speeds up, the cloud also rotates faster and faster. It collapses into the center to form a little star, and around that will be a disk. And so when we look at these stars that are just 1 million or so years old, amazingly, about the time humans first came on the Earth, these stars were forming. Every one of them has a disk around it, a disk around the size of the solar system, give or take a little bit here and there. And not only is the diameter of this disk right for the solar system, it has enough mass to make the planets in our solar system. So every young star, and throughout the Milky Way galaxy, a star is formed every year. So we have one star a year in the galaxy. Every one comes with the building blocks of a planetary system.
I see. The ancient stars, the early stars, would they have formed these kinds of disks also?
Probably every star that forms has to form with a disk around it.
Okay.
Now, the first stars will not have as many heavy elements, as we call them, beyond helium, as the stars that are forming now, because right after the Big Bang, most of the elements were hydrogen and helium, a little bit of lithium and beryllium, and maybe a teeny bit of carbon, but not much. And so they didn't have as much material to form, solid particles the way current stars do. And so, whatever planets they would make would have been very different from the planets that would be made now. This image, this nice image that was taken by the Hubble Space Telescope, is a big image of Orion, and we can look closer. So here is a close-up of 4 star systems in Orion. And so what you see when you look at these objects is you see a little dot in the center, and that's a newly formed million-year-old star. And it probably looks the way the sun did 4.5 billion years ago, when the sun was only 1 or 2 million years old. And you see that every one of these stars has a dark, disc-shaped, thing around it. And that's the disk. Okay. And so what you're seeing here is you see this sort of blue-red background, and that's the gas in the Orion Nebula that's being ionized by these very bright stars. And this disk that's around the star is blocking out the light from the background. So these are called silhouette disks because all you do is see them as a silhouette. You just see their shadows against the background. But these disks are about the size of the solar system. They have enough mass to make the solar system. And eventually they'll be planetary systems.
Okay, so it is inevitable that you will have planetary systems, maybe not 9 planets or something, but it's there.
Every star has the makings of a planetary system. And whether that happens or not is something that depends a lot on chance. What happens to the disk, what the star is like, what its surroundings are like, whether it's a single star or a binary star or a triple star, and there are quadruple stars. And so there are little systems of stars. And all of the different environments that the star and the disk can be in can affect the long-term evolution of the disk around the star. Okay. And so what kind of planetary system it eventually makes depends on all sorts of things that can happen between the very first instant the disk is formed and the next few tens of millions of years.
I see.
I'll show you what an artist's conception of a disk. So this is an artist's conception of a disk around a young star. The little yellow ball in the center of the disk is the young sun, only a million years old. And there's this big disk of mostly hydrogen, some helium, and lots of trace elements, and some very small dust grains, micron-sized dust grains, like you can see in a sunbeam, in your home. And those are mostly silicate, like quartz or something like that. And in the inner part, close to the sun, it's too hot for anything else but silicates to condense out of the gas. And farther out, it's very cold, and so ices can condense out of the gas. And so the grains in the inner part of the disk are rocky, in the outer part of the disk they're icy. And these grains are just sitting there, moving around the disk, orbiting the star just like the gas is. And eventually they start colliding with one another.
Okay, so that too is inevitable, that there will be these collisions, these build-up, these coagulations.
Right. And so two dust grains come together, and if they hit at low enough velocities, they'll merge.
Okay.
If they hit at too high velocities, they'll burst
bounce.
into lots of little pieces. If they come in sort of intermediate velocities, they might bounce off one another. But over time, the ones that come together at low velocities, that collide at low velocities, will merge and make, something that's twice as massive or 3 times as massive. And it's, I like to say that planet formation is works like the dust bunnies under your bed.
Yeah.
That it's an agglomeration process, and things, in a few weeks, if you have nice hardwood floors like everyone does in New England, you can get a pretty good sized dust bunny under your bed, and it's agglomeration of, your skin and hair and all sorts of stuff, just dirt and fly wings and various things that you don't want to know about. But in 2 weeks, you really want to get rid of this horrible thing under your bed. But imagine what happens in 1,000,000 years of agglomeration. And so in 1,000,000 years, a dust bunny can get pretty big, and that's how planets form. It's just this continual agglomeration process.
When the planets are forming, and you don't have specific numbers or anything, is there an order, for example, gas giants as opposed to rocky? Is there a kind of a sequence which comes first? Does it matter?
Well, we think we have an idea about this. And it's because when we look at star-forming regions like the Orion Nebula, and also there's a big star-forming region in the Taurus constellation, which if you go out, in a nice dark site in western Massachusetts or northern Maine or Vermont or someplace like this, you can see the dark clouds of Taurus where individual stars are forming, and they're 1,000,000 or 2,000,000 years old. And it's happening all the time, and every one of them has a disk around it. And in the disk, there's, the temperature of the disk gradually decreases outwards. The stars are about the temperature of the sun. The sun has a temperature of about 6,000 degrees, and so these stars are about 4,000. And so in the inner part of the disk, the grains and the gas are pretty warm. And so water, which is in the gas, can't condense out and form ice. So the grains are rocky, and they make rocky things. They agglomerate and become rocky, what we call planetesimals, which are about 1 kilometer or 10 kilometers across. And the planetesimals have enough gravity that they can deflect and attract one another. And so when objects become kilometer to 10 kilometer size, they grow a little faster. And so in the inner part of the disk, this is a rocky process. Big rocks are colliding. As you go farther out in the disk, it gets cooler because you're farther away from the sun. You don't get as much radiation. And so water can start to condense out onto the grains and make ices. And so now we have ice balls growing. So in the inner part, we have rocky balls. In the outer part, we have ice balls. And we think that eventually, the ice balls get bigger and bigger and bigger, and they will eventually get large enough that their gravity can keep hydrogen on their surface. So on the Earth, if you have a hydrogen balloon or a helium balloon, right, you let it go and it's gone.
It's gone, right.
And that's because the Earth isn't massive enough to keep the helium and the hydrogen in your balloon, on the table, say. So, because gravity attracts everything, but just the hydrogen, the helium, there's not enough gravity to keep the hydrogen and the helium bound to the Earth. But if the Earth were 5 or 10 times more massive, then and we would probably be a little smaller, because, but if the Earth were, say, 5 or 10 times more massive, when we had a helium-filled balloon, it wouldn't fly up.
That's right, yeah, right.
And if the Earth were 10 to 20 times more massive, the hydrogen balloon wouldn't fly up either. They would be bound. And so that's what we think happens to differentiate the Earth from, say, Jupiter. That Jupiter, which is a nice gas giant, and Saturn and Uranus and Neptune, are started as 5 to 10 Earth mass balls of dust, icy dust. So big balls of ice, they got massive enough, and then they started to be able to attract hydrogen and helium from this big gaseous disk that they're orbiting inside.
Just because of their mass, right. I see. Is it necessary to have a balance between these giants and the smaller planets like the rocky?
Yeah, right. Within these disks, it's very easy to make objects that are about the mass of Pluto to Mars.
Okay.
That takes about 100,000 years.
Okay.
And that where the Earth orbits and where Venus orbits, that takes 10,000 to 100,000 years. Around the orbit of Jupiter and Saturn, because they're farther away from the Sun, it takes a little longer, maybe 100,000 to a few 100,000 years. Then it gets tricky because we're not really sure how an object goes from the mass of Mars to several times the mass of the Earth.
Yeah.
In the inner part of the solar system, we have all these Mars mass objects, and eventually they'll collide and merge into a big Earth, and we think we understand that. Beyond the orbit of the Earth and Mars, where we have the gas giants, it's a little tricky, and we're still learning about how that process works. But we know that it has to be completed in a few million years.
Aha.
Because when we look at young stars, when we look at Orion, it's 1 million or 2 million years old, and we see disks around stars.
Yeah.
There's another region that you can see at night in the winter sky called H and Chi Persei, which is called the double cluster in Perseus, which is 2 star clusters with hundreds of thousands of stars. And they are about 15 or 20 million years old. They have no disks, essentially.
Ah.
So there are no, maybe
some
a
stars
few.
don't get to have disks. Okay.
Well, by the time they're 20 million years old, none of them have disks. They probably all have disks at 1 million years old.
Right.
But by the time they're 10 or 20 million years old, none of them have disks.
I see.
So we know that sometime between this 1 million year period and this 10 million year period, 10 to 20 million year period, that the disks go away. And we have a lot of clusters of stars, regions where we can get their ages pretty well. We don't know that it's, to the nearest year or something like that, but to the nearest, 500,000 years or something, we know these are 1 million years old, and these are 10, and these are 3. And we can see that the disks gradually go away. So we have a time frame based on the observations that we have of star-forming regions that the gaseous planets have to be made in a few million years. So somehow Jupiter has to get its 10 Earth mass core in, say, 500,000 years, just to pick a number.
It seems very fast.
It is very fast. And then it accretes this hydrogen and helium envelope in a few million years. And it has to do it very quickly, because if it doesn't do it very quickly, it doesn't have any hydrogen or helium to accrete anymore, because the disk is gone. And so you can imagine that can create a wide diversity in the planetary systems, that if Jupiter's core forms too slowly, then there's no gas to accrete.
Right.
And if it forms much more rapidly, then there's a lot of gas to accrete.
So you're dealing with probabilities a lot.
So you're dealing with probabilities, and what are the initial conditions, and what happens. It's like a person growing up. You have a decision. Do you go to the baseball game tonight, or do you listen to your favorite concert group with your friends? And so those different choices change the kind of person you are.
Yeah.
And that happens to planetary systems. They're not people, but different things happen to them that change whether you end up with an Earth mass planet, or a Mars mass planet, or a Jupiter mass planet.
One thing on a planetary system, we have an idea everybody is in their right place, but they move. There's a possibility that they move. Is that correct?
There's a lot of what we call chaos in the system.
Okay.
So when we start out with this nice disk of gas and dust, a given particle has a pretty well-defined orbit.
Yeah.
And it has a pretty circular orbit, so it has no eccentricity to it. So it's always pretty much at the same distance from the star.
At the beginning.
At the beginning. Now, as these things grow and they get bigger and bigger and bigger, they have their own gravity. And so once you have, say, several Pluto mass planets or a bunch of Mars mass planets, they start jostling one another around. I mean, like going into a crowded subway system, everybody wants to get on the car, and so people jostle to get in.
See.
The planets, because they have gravity, are they're not elbowing each other away,
Right.
but their gravity
It's affecting.
goes over a large area, and it affects their neighbors. And so then their orbits start to be more eccentric, and then the orbits sometimes can cross. And there's a period in the growth of planetary systems where the orbits are actually chaotic, where if you asked, well, what is the actual orbit of this Mars-sized rock going around the sun, you wouldn't be able to tell because every year or every 2 years, it has a different orbit because it's being jostled by all these other planets that are trying to form. But eventually, let's say around the orbit of the Earth, you have maybe 20 or so or 30 or so lunar mass or more massive objects that are colliding over time to form the Earth. As they collide and jostle one another around, eventually there's sort of a king of the hill.
Yeah.
And it gathers up all the others over time, and it becomes the Earth. And it clears out its orbit, and as it's clearing out its orbit becomes more circular. And so the orbits go from being circular in the beginning to chaotic in the middle to nearly circular at the end.
I see.
And during this time, when the orbits are becoming organized of the planets can move radially in or out in a process that's become known as migration. And sometimes the migration can be very fast, and the planet can migrate actually into the star or very close to the star. Sometimes it can migrate out. Sometimes it doesn't migrate very much at all because a gravity of a planet outside its orbit may keep it from migrating too far, or a planet that's inside might push it away. And so gravity is a very funny force because we think of gravity as attracting objects.
Yeah.
But gravity also, even though it's always attracting, ends up repulsing some things. And so, the Earth keeps its orbit clear because it pushes other things out of the orbit, and Venus keeps its orbit clear, and Jupiter keeps its orbits clear.
Right. Eventually. Eventually.
At some time, yes.
Yeah, right. That's very interesting. Now, eventually, also, some of these systems develop habitable zone areas, right? But maybe not all of them from what they've discovered. What is the story on that?
Well, the habitable zone, just to make sure we're all discussing the same thing, is a region we've decided, being human-centric, is conducive to life, the life we understand. And so we want an area or a volume around a star where you're not too close to the sun or the star, so it's not too hot, and it's not so far away from the star that it's too cold. And so what we call the habitable zone is the region where we think that if you put an Earth mass planet with oceans and some kind of atmosphere, the temperature would be conducive to the life that we understand. Now, it could be that the real habitable zones in the universe encompass everything because we don't understand enough about what life is. But from what we understand as life, we have this habitable zone, and it extends more or less from the orbit of Venus to the orbit of Mars, give or take.
Right.
And if the sun were hotter, then we would move that zone farther away. And if the sun were colder, we would move it closer in. And so stars have a range of temperatures from much cooler than the sun to much hotter than the sun. So there are a range of these habitable zones from very, very close to cold stars to very far away from hot stars.
Okay.
And now, there's no guarantee that a planet will actually form within the habitable zone. It may be that in all of this, the dust bunnies growing, the agglomeration process, the chaotic activities that go on as planets are trying to form, that a planet will will end up just inside the habitable zone, and another one will end up just outside it. And in the star systems where we've identified planets, most of the stars are inside, or most of the planets around the stars are inside this habitable zone. So we now know of about 2,000 planets, give or take.
It's amazing how fast that accumulated.
It's amazing how many planets there are now, when just 2 decades ago there was essentially none. But most of them are inside what we would call the habitable zone.
I see.
So they're too close to their central stars to be what we would think of as conducive to life.
Right.
Now, there are almost certainly a lot of planets within the habitable zone.
Yeah.
But it's also not guaranteed that a planet within the habitable zone will be an Earth-like planet.
Right.
It could be something like Mercury, which is the closest planet to the sun, but if you moved it to the Earth's orbit, it would be the right temperature for life, but it has no atmosphere.
Yeah.
And it has no water.
And it's not going to get any.
And there's no way for it to get any more. And so that would be an inert planet from our way of thinking.
Yeah.
And so you're not guaranteed that you have all these ingredients that we think of as necessary for life, that you have a planet about the mass of the Earth, you have water, you have an atmosphere, you have all this stuff that you need.
Yeah.
And you could have a planet that has all of those characteristics, but could be too far away or too close.
The business of how astrophysicists evaluate gases around why is that so significant? Why do you go looking for what kind of gases are on a planet?
When we look at these gaseous disks around young stars, we see the gases that we know and love in the universe. We see carbon monoxide, we see carbon dioxide, we see water. So we know that in this molecular disk orbiting the star, not only is there hydrogen and helium, but there are these simple molecules, ammonia and methane, and that are the building blocks of more complicated molecules. And people are finding more and more complicated molecules within these disks. So when we look for a planet, whether it's Pluto or Jupiter or the Earth, we want to know what its composition is and what how, and that tells us how the planet was made. So if a planet has lots of methane and no ammonia, it tells us one thing. And if it has a lot of ammonia and no methane, it tells us something else. Because those two molecules condense out of the gas at different temperatures. And as I remember, ammonia condenses out at a colder temperature than methane.
I see.
And so we would think that something that has more ammonia should be formed in a colder region than something that has more methane. And if you only see water ice but no methane ice or no ammonia ice, then maybe it was formed farther in. So we look for these signals of where in the disk this planet came from.
So that's primarily what that tells you.
That's what people
origin,
start
more
with.
or less.
Right.
Okay.
So you look at Jupiter, and it has nice methane in its gaseous atmosphere, and so that tells us something about how Jupiter formed, and it has other elements in it, and we try to piece together the history by looking for not only ammonia and methane, but every element, because every element tells you a little bit about where and how the system formed, at what condensation temperature you got this as opposed to that.
I see. So that's indispensable information that you can get.
Right, because every system, every planetary system or every young star system with a disk that we look at is a snapshot. And so when we look at the disks in Orion, we see a bunch of disks as they are now, and they're all a couple million years old, but we have no idea what those disks looked like 300 years ago and 300 years from now. But we try to find another star-forming region that's a little older than Orion, and another one that's a little younger than Orion. And so we get all these snapshots, and our goal is to make a movie. You know, we would like to make the star formation, planet formation movie, and we start with stars that are, 10,000 years old. And we look at the sun that's 4.5 billion years old, and we look at stars that are 10 billion years old, and we get snapshots of all different levels of planets and debris disks, which are the debris left over from planet formation. And we just try to string this all together in a way that makes sense.
Within that disk, like within our disk, there is material from supernovae, apparently because of the heavy elements that we find in the Earth, like uranium and gold and so on. And are those typical in disks? Can you identify that?
Well, we think that the basic elements like gold and silver and uranium are probably pretty common.
Okay, because I thought those were very rare.
But there are, they're rare in the sense that they're not a big constituent of the solid material, but they're probably universal.
Okay, so you're going to find them throughout
you won't find them in big abundance. I mean, no one should go out to some other star system think they're going to get 10 times more gold or platinum in it.
We should be mining it,
but there will be gold and platinum and silver in every planetary system.
Okay.
But what's interesting about our solar system, and is a way that that our elements of the solar system that we've used to understand the formation of the solar system are various radioactive elements. Now, uranium is a radioactive element which has a very long half-life. But there are other, and so that's why we still have a lot of uranium today, is because its half-life is long compared to the age of the Earth. Not longer than the age of the Earth, but long compared to it, so that there's still a lot of it around. But there are other radioactive elements that have very short half-lives, ranging from days to millions of years to hundreds of millions of years. And the ones that are just a few million years can give us a really good clue about how the solar system formed. So there's an element called aluminum-26, which is radioactive, and it has a half-life, around 1 million years. And we see the decay product, the so-called daughter nucleus of aluminum-26, in meteorites.
I see.
And by looking at the abundances of the non-radioactive elements compared to the products of radioactive decay, we can date the solar system very precisely.
That's how they've managed
and in fact,
to date ours.
We can date meteorites to within a fraction of 1 million years.
That's amazing.
Because we can see the decay products of various isotopes of aluminum and iron and various other things. There are 3 or 4 of them, which I can't remember all of them now. But they give us a picture of when various things formed and the timing of this particular class of meteorites as opposed to that particular class of meteorites. And that, again, allows us to fill in the pictures of this movie. And so supernovae, which spew out all these radioactive elements, and very evolved red giant stars, which spew out another set, if there was one close enough to the solar system, it will drop aluminum-26 into the solar system or the planetary system. And if there wasn't, if the planetary system forms without a nearby supernova, then it won't have this aluminum-26, and the inhabitants of that planetary system will have to find other ways to date the system as precisely as we can date ours.
Right. That's wonderful that they could tell all of that just out of a few elements.
It's amazing,
really.
Yes.
Right. All right. Well then, finally, Mr. Pluto.
Right.
And you did a wonderful, I guess it might have been the Harvard Gazette or something. It was a very nice interview with you there about Pluto. And this was just at the time of the flyby.
Just before the flyby,
so people were really all psyched. Are you one of those people that's very excited about Pluto, and if so, why?
Well, I'm very excited about Pluto because I'm not a geologist. So,
Right.
It's a lot of what's a lot of the images that have come back from Pluto are just amazing.
Like the mountains.
Yeah, the mountains and the chasms
Yeah.
and the what seems to be ice flows.
Yeah.
And I look at it in a little bit different way than the public,
Sure.
but not a big different way because I'm not
Right.
a geologist
Right.
and I don't study the surface evolution of planets at all. But it is fascinating that there can be, such
a little
tall,
tiny planet.
well, yeah, it's a very tiny planet, and it's very tall mountains.
Mm-hmm.
And compared to the size of the planet, you would have to climb 2 to 2.5 times Mount Everest
Yeah.
to climb a comparable mountain
Isn't that
on
amazing?
Pluto.
Yeah.
And the chasms are 4, 5, 6 miles deep. Several times the depth of the Grand Canyon on a world Charon, which is only 500 or 600 kilometers across. So, the chasms are really deep compared to the size of the planet, and it's just amazing.
Right. So that's the big thing.
So
with you.
that's really fascinating.
Right.
In terms of my work,
Yeah.
it's not as interesting because it's not what I do,
Right.
day to day. I
Right.
don't really worry about how the geology of Pluto should be different from the geology of Charon.
Right.
But I'm fascinated with the moons. So Pluto, Pluto Charon itself.
Maybe better
So I'll
explain
back up,
to it.
I'll back up on
yes.
that. So we have Pluto. Pluto is about 1,000 kilometers in radius. So it's a sixth the size of the Earth.
Mm-hmm.
And it has a companion, a moon, called Charon, which is about half the size of Pluto. So our moon is something like an eighth or so, a seventh,
A proper size.
a very small fraction of the Earth, a quarter or something like that. I think it's a quarter, give or take, a quarter or so of the radius of the Earth. Charon is half the radius of Pluto. So it's only a tenth of the mass of Pluto, and the moon is something like an 80th the mass of the Earth. And it also, orbits very closely. So the orbital period of Charon around Pluto is 6 days. So if you're sitting on Pluto and you construct your month the way people on Earth do by the orbit of your moon, the moon orbits the Earth around once every 30 days or so. And on Pluto, your month is 6.5 days long. And like the moon, Charon is tidally locked to the Earth, which means that the one hemisphere of Charon is perpetually facing one hemisphere of Pluto. But unlike the Earth, Pluto's hemisphere is also locked. So the same hemispheres of Pluto and Charon are always facing each other.
And that's unusual.
That's
as far as you...
it's unusual in our solar system to have such tidal locking because
they're both
they're such similar masses.
Right.
And it's thought that they came into being this way by a big collision.
I see.
That Pluto formed somewhere in the solar system, Charon formed somewhere else, and they collided, and they became a binary. And while they became a binary, in this collision, Charon kicked up a little bit of Pluto's surface, and Pluto kicked up a little bit of Charon's surface, and there was some debris around them. And out of that debris, 4 moons came into being, 4 little moons.
Isn't that amazing?
It is amazing. And they're tiny little things. They're just a few kilometers across. So they're 1 million times, give or take, less massive than Pluto and Charon. And they orbit pretty closely, and there are 4 little ones. Since I study planet formation, I'm sort of fascinated with, how often would this kind of collision happen? What would the outcome be? And so my colleague and I, Ben Bromley, did some calculations about how this might work.
Right.
And we predicted that there would be some additional moons outside the orbits of the current moons. So the outermost moon now is called Hydra. All of Pluto's moons have to be named after something associated with the underworld.
Yeah.
So Hydra is the outermost moon. And it orbits, I think, with a period of around a month, an earthbound month, 30 or 40 days. And we thought that there might be some smaller moons outside the orbit of Hydra. So we're hoping that the New Horizons team will, I know they took pictures of the whole system, and we're hoping that eventually they will find some other moons, which will test our theory.
But that's your thing, isn't it? This to develop these kinds of systems that will predict this sort of thing. So you must be in heaven waiting for this.
That's our idea, and I can show a picture of Nix here, Nix and Hydra. If we can put the slides up.
There it is.
Again. So these are two of the moons. These are two New Horizons images from the moon. Nix is the second closest little moon. So coming outward, Styx is the closest, and it's much smaller. And then Nix, and then a moon called and then a moon called Kerberos, like Cerberus, but Cerberus was already taken. Somewhere in the solar system. I think there's an asteroid or something that's called Cerberus. So they had to have another name called Kerberos. And Hydra is the outermost one. So you can see that they're not round balls, but neither are they, funny jagged edges. And so, they have some round parts, and they look sort of like a potato or a football or something
weird.
like that. And you can see that there are dark and bright portions to them. And so, the geologists will try to understand what all the dark and bright portions mean, and what we do as theorists who try to calculate how these things came to be and how they evolve, we'll take that information and put it back into our theory of how the moons formed to try to get something that has reasonable shapes from the point of view of the observations.
Right. Well, just one point on that is that to qualify as a moon, all you need to do is go round and round, right? You don't need to be round.
You don't need to be round. That's right. All you need to do is go round and round a planet. That's right. Yes,
all right.
That's right.
Do they become round ever, do you think, or do you need a certain mass?
These are probably not quite massive enough for their self-gravity to make them round.
Yeah.
So Pluto and Charon are very round.
Yes. Okay.
And so they have enough self-gravity that you throw enough Hydras and Nixes at them, they'll find a way to become round at the end of that. And it's what in between Nix and Hydra and Pluto and Charon, how something becomes round depends on what it's made of and how molten it is or liquid.
Yeah, I see.
And so
factors again.
Right. So in the early part of the Earth's life, the collisions were so frequent that the Earth was a big molten ball. Mm-hmm. And if the collisions were not quite as frequent, because we think the Earth formed over several tens of millions of years, but if the Earth formed over several hundreds of millions of years, say, it would not be molten because the collisions wouldn't be fast enough to keep the heat of the collision. Because every time something collides, it makes some heat, and the Earth gets big enough that it can trap that heat. And that's why we have a molten core and a liquid mantle and all this other stuff. And so, if the collisions are slow enough, then something that is less massive might not be so round, whereas if something accreted very quickly and was very, very molten, even a small thing could be very round.
Right, I see. In our remaining time, we're running out of time, I wanted to talk about your work.
Well, so what we try to do, and I'll try to give an idea of why we do what we do, is I mentioned that we have this movie that we make. And so observationally, we have a lot of images or snapshots of the history of planetary systems. And we need some way to organize those. And we could just organize them based on the ages of stars, and so we do organize it that way. Mm-hmm. But there are a lot of things that happen that might make one system seem younger than another system. Mm-hmm. And I can give you one example. There are 10 billion-year-old stars that have lots and lots of debris around them. And so, they have these big debris disks. And you can actually see the solar system's debris disk. If you go to a nice dark place like northern Vermont or northern New Hampshire or Maine, and you go out just after the sun is set, you'll see a band of light coming up from where the sun's set, going up like a cone, and that's called the zodiacal light. And that's a bunch of millimeter-sized particles in the disk where all the terrestrial planets are. And when we observe those dust particles around another star, we call that a debris disk. Now, our solar system is about 100 times too faint to be detected by our current instrumentation. But there's a star that's twice as old as the sun that has a disk of debris that's 10,000 times brighter than the sun. And so there's something, it looks young compared to the sun, which is sort of, from our point of view, sort of dead in the sense of it doesn't have this debris. The solar system is formed, and so it's not very interesting from the point of view of evolution anymore. And so we need some organizing principles to tell why is this 10 billion year old star different from the sun. And since we can't do experiments, we do calculations. And so we make simulations on the computer. And this is a characteristic of astronomy that dates back 100 years now, because astronomers 100 years ago were trying to understand the structure of the sun. So they didn't make computer models, but they made theoretical models, and then they did lots of mathematical calculations on pieces of paper, to figure out what the structure of the sun would be and how long it could live and things like that. And so we follow in this tradition of trying to construct a theoretical model, a numerical model, for how planets form and how they evolve. And so in doing that, we put a bunch of physics into a calculation. We solve a bunch of equations to see how this initial disk that I described earlier, this disk of hydrogen and helium and dust grains, how will it evolve? And then we take snapshots of this disk too. So, because we can't look at the evolution every second, we take a snapshot of it every 100 years or every 1,000 years or something like that. And we try to match our snapshots to the snapshots that observational astronomers get when they take images with Space Telescope, or when Pluto flies by, New Horizons fly by Pluto. And so we constructed this code to understand this long-term evolution so that we can put the observations in context and then make predictions of what, for this system, if you look at it in more detail, you should see this. And so, as I described for Pluto, we predicted there should be more moons.
Right.
And we have a set of reasons why there should be more moons, and based on these calculations. And so the calculations are, it's a bunch of, it's 10,000 lines of code. And it does, it does what's called a coagulation calculation. So we calculate this agglomeration. And then once the objects get large enough, we follow their trajectories around the star. And so when we have enough of these, what we call N-bodies, that interact gravitationally, we follow how they interact and how they move one another around and things like that. And so we can make predictions of what things should look like.
And this is now an indispensable tool, especially your orchestra, I think, is it the number one system for this, because it predicts very well.
These kinds of codes are really important for trying to understand how things came to be in our solar system and other solar systems. And we make predictions. Some of the predictions turn out to be true, some of them not.
Of course.
And so, based on the new data that people get, we say, we didn't understand this aspect of it. How do we fix it? And so we have to think about what physics have we missed, what chemistry have we missed, what geology have we missed, whatever it is that's the problem, and we try to fix it, and then we do a new set of calculations, and we ask, can we match the observation now? And sometimes you can and sometimes you can't. So you twiddle with it and you keep changing the physics, because there are a lot of things we don't know, until you get a match. And then you say, now that we have a match to this, we predict a new set of predictions.
Right,
Go out
right.
and look for these.
Yes.
Sort of an art,
Yeah.
in a way, to construct these codes, because George Wetherill was a scientist who started using these kinds of codes for planet formation, decades before I started. And he said you have to be careful not to put the whole kitchen sink into the code. That you have to understand what's essential and what's not.
That's why you say it's an art.
Right, because you say, oh, I could put this in, but I'd like the calculation to be done quickly enough. And so, our computers aren't fast enough to do the calculation of your dreams, because you can't put everything that you would like to put in and get the calculation finished in your lifetime. And so you have to pick and choose what kind of physics you put in, and to do that you have to decide, well, what's important? What am I trying to understand? And okay, maybe I won't worry about trying to understand this because I think it involves too much of intricate things that I don't understand to put into this code. So there's an art to it. There's a lot of science into it that you have to decide exactly how to solve things, and that's but you have some choices, and some of that is intuition and art rather than well, it has to be done this way. And you see these codes every day.
Yeah.
I mean, if you do a Google search, that's one of these codes. It's a different code. It's a different kind of code.
And how fast it is.
But they too have to make decisions of what goes into the search algorithm and what doesn't. And sometimes they make mistakes, and sometimes they just get it right on. And so traffic patterns, air traffic control, all of these things use very sophisticated codes. And you want high quality practitioners to be doing these things, because unlike our planet formation code, some of them really impact people's lives every day in a way that's pretty profound.
Right, but so have you. And you're given a great gift, that because you're really at it seems like a wonderful time in history to be doing this kind of work. There's just so much.
Well, we're at a time where the understanding is growing, and, and we can make some sizable contributions to the flow of this field at this time.
Yes, it was wonderful to talk with you. I hope we'll have another chance. We run completely out of time. I do thank you very much for joining us tonight. Thank you.
Well, it was my pleasure. I really enjoyed it. I hope we can do it again too.
Absolutely, absolutely.